This video is on optimization problems. So we've looked at minimum and maximums of functions. This is applying those idea of that every function has a minimum and a maximum to some real world situations. So the example I'm going to use here, a manufacturer wants to design an open box that has a square base. So it looks like this, sort of. And it's open on the top. Well, so far so bad. No, that's not too bad. So here's the base, and it's a square, so that we know that the length and the width are the same, and then it has some height. So a manufacturer wants to design an open box having a square base that has a surface area of 108 square inches. So that's the amount of material that's going to be used to make the box. So that's sort of a restriction on this problem. Using a certain amount of material to make the box, they want to find the dimensions that produce a maximum volume. So they want the volume to be maximized. So, you know, if you have 108 square inches of material and you fold up the sides, you can get different boxes, you know. It could be sort of shallow. They're still having a square base. Oops. So these still being X, same size here. It's just shallow, so it's going to produce a different volume. So the same amount of material, depending on how you fold it, is going to get you different volumes. So we want to maximize the volume. So we know that the volume of this thing, volume of a box is length times width times height. So x times h. So the volume equals x times h, or x squared h. And this is what we want to maximize. And we call this our primary equation, because that's the one we want to maximize. The fact that the surface area has to be 108, surface area is length times width for the base, right? So we have x times x, that's for the base. This side right here would be x times h, so we would add that, x times h, and you've got 4 of those, 1, 2, 3, 4, all x times h. So I'll just say 4 times x times h, or 4xh. So another way is to say this is x squared plus 4xh, and that's the surface area, and that has to be 108 square inches. So that's this is called our secondary equation, because this is given to us. We know that the surface area has to be 108. We know the formula for surface area. It's the area of all the sides added together. The base is a square, and the sides can be, as long as x times h, this is x times h here. All 4 of these would be the same, because it's a square base. So we have a primary, we have a secondary. We have to remember this is what we're trying to maximize right here. The problem with this, you know, when we've taken derivatives and set them equal to 0 to find critical points, and then those critical points sometimes yield minimums and maximums, we only had one variable. We have 2 variables here. And we don't want that. We want to have everything in terms of, let's say, h. So we can take this secondary equation and we can set it equal to h, so that h is by itself, and then we can substitute that back into the primary. So solving this for h, let me see how we're going to do this. Yes. I'll subtract x squared from both sides. 4xh equals 108 minus x squared, and then divide both sides by 4x. So now I have h equals, am I going off the video? H equals, so I subtracted x squared from both sides, dividing by 4x, and that leaves me, I'm just going to leave it as 108 minus x squared over 48x. So this is H. So now I've taken my secondary equation, and I just solved it for H so that I got it by itself. Now I can substitute this back into my primary, and then I'll only have one variable. So instead of calling that x squared H, I'll call it x squared 108 minus x squared over 4x. And I can reduce that. I can cancel this x with one of these and then distribute this, and I would get, well, I'll say 108x minus x cubed over 4. Another way to write that, if I divide these, I can get 27x minus x cubed over 4. Remember, this goes with each of these, so we have to divide that by 4 and that by 4. So here's my new function. So this is a composite function. This function is made from two other functions. It's a function within a function. So I took my secondary, solved it for one of the variables, plugged it into the primary. So now that I only have not only do I only have one variable, I also have my primary that I'm trying to maximize, and the restriction of the surface area is embedded into the new problem. And so this is what we're looking at. This is our new function. All we have to do is take the derivative of this, set it equal to 0, and we'll find the minimum or the maximum. In this case, it's going to be a maximum volume with the restriction already inside the problem. So the derivative of this is 27. This is 1/4, and multiplying by 3, so minus 3/4 x squared. Set that equal to 0. Move this to the other side. I get 27 equals 3/4 x squared. Multiply both sides by 4/3, which gives me 4 times 27 is 108. Divided by 3 is 36. Take the square root of both sides. I get x equals plus or minus 6, but we know that the length of a side of the box can't be negative, so it's got to be positive 6. So when x is 6, it maximizes the volume. So if I go back to this equation here, I can figure out what the h has to be. So if I plug the 6 in here, 6 squared is 36 from 108. How much is that? That's 102, 172. 4 times 6 is 24. So that gives me 3. So h would be 3. And now my maximum volume is going to be a 6 by 3. X is 6, so the base is 6 by 6, and the height would be 3. And the height would be 3. And that maximizes the volume. It gives me the most volume, so 6 times 6 is 36, times 3 is 108. And that's a optimization problem.